Hello, my name is Marat Avdyev. Today we consider Fermat's last theorem for billions people age of 12 plus. Here is the historical review. Fermat's last theorem was formulated by Pierre de Fermat in 1677. This theorem was proved by Professor Andrew Wiles of Princeton University in 1994, but his proof consists of 140 pages. But how about people who don't know number theory? Here is essential skill in math. Now you can see a cube, a hypercube for n space, pyramid, and the formula of volume of pyramid, Pythagorean triples, a square plus b square equals c square, and the square of triangle, base, height, and coefficient 1/2. That's enough. One moment. Square root 2 is irrational number. Please read it. Let us consider hypercube as a set of shell, a set of layer. For instance, 3 power 2 plus 4 power 2 is equal 5 power 2. Pythagorean triple. Here you can see it. A set of hypercube 1 power n and S1, S2, Se. Let us consider two cube, n cube, A small, B middle, and C large. All of them correspond to C power n, B power n, and A power n. Suppose this numeric number exists, and A power n plus B power n equal C power n. Now, one can see the main properties for hypercube. Volume as A power n, surface 2n multiple A power n minus 1, for square, for cube, for tesseract, and so on. The number of vertex equals 2 power n. Total number of faces, edges, and of g dimension is the formula 2 power n minus g multiple binomial coefficient c, g, n, where this coefficient one can take from triangle of Pascal. Let's go on. Suppose we have 3 cube, A small, B middle, and C large. A small, that is the set of 1 power n and k layers. Additional L layers we have B middle, and one more additional M layers we have C large. The Fermat's last theorem state that V1 equals V3. This is a necessary condition. Here you are. A equals V1 in n-dimensional space, B equals V1 plus V2, and C equals V1 plus V2 and V3, where V means volume. All this in I power n integer number space. analogy of real number space Rn. This is the necessary condition. All the layers should be continuously and full. For instance, this is not hypercube. This is hypercube, dimension 3. But this is layer S1 in one notation, in our notation. Before we continue, let us consider linear similarity, alpha coefficient. This is the formula. For instance, for cat mustache, alpha coefficient, simple alpha. For wings of butterfly, the coefficient alpha square, and for body of Apollon, alpha cube. Let's go on. If we cut our cube by virtue of 2n hyperpyramid, here you are, the case n equals 3, and on the right the case equal to square root. Here above is the formula. Limit the volume of SE divide the volume SG equals, here is binomial coefficient. Approximately it is equal to surface of this layer. In limit, the approximation is distinct. Here is the definition of layer. What is layer SI? SI, it means set B minus set A, where B equals B power n, A power n. And the edge of B is I plus 1, the edge of A, I power n. Here is the formula, binomial coefficient. Look at this counter from O to n minus 1. It is very important, n minus 1. So the formula for hypercube is 1 power n union S1 union S2 and so on, Si, for case of I plus 1 and cube I. For instance, for n equals 2 square root, the surface of 3 power 2 is 6. It means perimeter divide 2, because the vertex is in the center coordinate situated in vertex of each cube. The volume of S2 equals S3 equals 4 power 2 minus 3 power 2 equals 7. Here is the difference of one cube, blue cube. Dimension of surface is n minus 1, and dimension of layer also is n minus 1. Let's go on. Linear similarity, alpha coefficient. It follows if and only if condition A power n equals B power n if and only if A power n minus 1 equals B power n minus 1. Here is the faces, the volume n minus 1. Here is the faces, the volume n minus 2. We suppose that n enough, more than 2. Here is the picture. And we have the layer Si equals layer Sg if and only if E equals G. There are no another alternative. Let us consider cube. Here you are. The cube has symmetry form. Each face of it equal to another. So let we swap the layer in large cube, C large cube, and some layers in A small hypercube. Because of homogeneity of space, its operation will conserve the symmetry property. Let us try it. Is it possible or not? Really, it is not possible. For instance, for case alpha similarity equal to, here surface should be transformed into 4 surface for n equals 3. I mean cube in 3-dimensional space, because the volume of surface of hypersurface is in proportion of n minus 1. So we have for any layers the volume of hyperpyramid layer of hyperpyramid is equal sum of layer. Here is the zone of BC large cube, yellow. And here is the layers from A small hypercube. Equivalence. Here you are. Binomial coefficient, this subtraction t power n g, v power g equals another. This is the subtraction between layers t and v. Here one can see condition. Interval 1 from 1 between 1 and k, another interval between k plus l plus 1 and k plus l plus m. Above we described these variables k and m layers. Consequently, if where v1 equals v3, here you are, for layers Sg and Se plus the volume Sg minus 1, consequently, continuously, unresolvable equilibrium, where p total times is greater than 1, but p we suppose is integer number due to symmetry of hypercube. Here you are, p, the number of layers in small hypercube, nested hypercube to each other. Let's go on. Here is the layer, green zone, A small, middle, yellow, and C large hypercube. Equivalence of volume. That means that 1 power n is not equal to any of layer. Let us consider 2 power n. 2 power n hypercube has volume less than difference between any layers. You can test it. The subtraction of difference between layers and 2 power n hypercube, that equivalent 1 plus 1 power n. Here is the formula. Be accurate. We should be accurate with the index from O up to n minus 1. This is greater than O. Special case, n equals 2. This is the square. In this case, this formula transforms to e power 2. And one can find Pythagorean triple. This is special case. But for any another n greater than 2, we deal with figures that has broken irretrievable defect of symmetry. For instance, any operation of this figure do not restore the cube, only absence vertex. This is 2 power 3 power cube. So the expression c power n minus b power n is the set of layers, but not a cube. Look, on the left one can see the set of layers with dimension n minus 1. This figure corresponding to this formula has fatal defect of symmetry. On the right, one can see cube power n, a power n. That means the figure is a cube in n-dimensional space. His dimension is n, and this figure has symmetry property. In logic, we have directly opposite statements. So there are such A, B, C in I power n space that correspond to this formula. That's enough. Fermat's last theorem has been proved. Here is 2 pages in mathematics. That's enough. Here is my biography. Thank you very much for your attention.